Okay, so let's talk about the first law of thermodynamics. This is one of the most important laws surrounding the idea of heat transfer and the conversion of heat into other forms of energy. Now, specifically, whatever amount of energy you have, call it du. Okay, so changing internal energy. In fact, that's what we call this thing, changing internal energy. Whatever internal energy your system has. That can come in the form of heat, dq, or in the form of work, dw. And the idea right here is that at a given temperature, you're going to have a constant amount of internal energy associated with your reaction or your substance. But that amount of energy can be distributed into heat and work. And moreover, heat can be used to change into work and perform some amount of work on something, or work can be used to ultimately end up with heat. These two are interchangeable with one another. They're basically forms of energy, different forms of energy, but energy nonetheless. Now their combo, however, has to remain constant depending on the temperature at which this is carried out. This is the equation format of the first law of thermodynamics. What you might have heard and read in the past is that energy is neither created nor destroyed, only transferred from one form to another. And that's in essence what this equation is showing you. The internal energy is a constant value at a given temperature, and it can only be transformed from heat to work or from work to heat. So in essence, this is the first law of thermodynamics. What we're going to do in this lesson, however, is we're going to actually utilize the equations to calculate the values of heat, work, and internal energy. In order to do that, we have to look at three specific instances at which a measurement can be performed on a gas. The first one is a situation in which the volume is constant. So you have a sealed container, the volume is not changing at all. All right, now, under that premise, one thing that can be said is that for the heat is given by MCAT. Now, in the case where the volume is constant, however, we do not tend to use the specific heat capacity, but rather a similar relative of it, specifically the heat capacity at constant volume. Now, the heat capacity at constant volume has units of joules, mole, Kelvin. So you don't multiply this by the mass, but rather by the number of moles of the gas. So you have moles multiplied by the heat capacity, multiplied by the change in temperature, and that gives you the change in heat. All right, for the work, on the other hand, and restraining ourselves to gases and only gases, the work is given by the negative pressure times the change in volume. But here I'm going to go on the assumption that the pressure is variable, so I'm going to use negative nRT ln of V final over V initial. That will be the actual change in work under variable pressure but constant volume. If the volume is constant, V final and V initial are equal to each other. And that means that now you have negative nRT times ln of 1. And whenever you have the logarithm of 1, that's the same thing as saying 0. So in essence, by keeping the volume constant, there is no work. You don't do any work on the system, and the system doesn't do any work on the surroundings. The work is 0, which is rather interesting to look at it from this point of view, because technically speaking, you could be doing a lot of work. You could be doing a bunch of homeworks, preparing for your exam, and as long as your volume doesn't change, technically speaking, you haven't done any work. Kind of trippy to think. All right, but as a result of the first law of thermodynamics, since the internal energy is the combo of the heat and the work, automatically the internal energy in this setup has to equal N times CV times dt. And this particular relationship is one that I'm going to utilize heavily when it comes down to the first law of thermodynamics. Specifically, the idea that the internal energy depends on temperature and temperature alone. And as you'll find out, if you don't change the temperature, something very specific is going to happen about the change in internal energy. But for now, under constant volume, du equals dq, and both of them are given by ncv dt. Alright, so let's do a quick problem that depicts this situation. We have a gas, 0.75 moles worth of that gas, and the temperature is being raised from 288 Kelvin to 400 Kelvin. The volume is constant, and the pressure is 1 atmosphere. And right here I'm going to go under the assumption that it's constant, but as you'll find out in a second, it really doesn't make a difference. We're also given the heat capacity at constant volume, which is 3.05 joules per mole Kelvin. And we need to use all of this information to find out the values of du, dq, and dw. Alright, now, what I typically do in problems of this sort is to go after the work. That you have equations for, so you can just go ahead and try to solve it. Alright, so for the change in work, here I'm gonna go under the premise that this is constant pressure, but as you'll see, this will not affect things at all. Now, under constant pressure, the equation for work is negative pressure times V final minus V initial. Because the volume is constant, as being told in the problem, V final minus V initial is simply 0 liters, right? They cancel out. And any pressure multiplied by 0 is automatically going to give you 0. In this case, the units are atmosphere liters. If you were to multiply this by 101.325 to change it into joules, you'll end up finding out, unsurprisingly, that this is still 0 joules. So there is no work done because the volume is constant. And technically speaking, you don't even need to do all these calculations. If you just remember that the work is going to be 0 when the volume is constant, you got that answer. Now, step 2. I'm going to go after the heat now. We have a heat capacity, we have the number of moles, and we have the change in temperature. So we're going to utilize our equation. Moles times heat capacity at constant volume times the change in temperature equals the change in heat. So we input 0.750 moles, 3.05 joules per mole Kelvin, and 400 minus 288 Kelvin for the change in temperature. All the units will cancel out except for joules. And in this setup, we find out that the change in heat is 256 joules. Okay. Now, lastly, due to the relationship between internal energy, heat, and work, we can simply carry out that summation. We know now that the heat is 256 joules. The work is 0 joules, so automatically that means that the internal energy is 256 joules. And like that, you find out the 3 values for heat, work, and internal energy at constant volume. We have 2 more parameters that we need to examine, but I'm going to save those 2 parameters for the next video.